Hello my dear students. So in my last class I was explaining about Carnot cycle. It is a second law of thermodynamics. So in second law of thermodynamics we discussed about heat engine, what is meant by heat engine. So Carnot cycle or a Carnot's engine, it is also called as Carnot's engine. So it is also a heat engine, which is an imaginary Carnot's engine. So where a series of chemical reactions or a series of operations which are going to take place, and we call it as the Carnot's cycle. Okay, so there we saw mainly four different steps of reactions that are going to take place. So out of four different steps, so two are isothermal and two are adiabatic reactions or processes which are going to take place. And the first two steps are we saw that where the ideal gas which is taken in the cylinder, which is kept in the system, so it is going to expand. Okay, so in step 1 we are going to see that, so there the expansion of ideal gas is going to take place isothermally, and in step 2, so the expansion of the ideal gas is going to take place in adiabatic condition, and in step 3, so the compression of the ideal gas is going to take place in the isothermal condition, and in step 4, so the compression of ideal gas will be carried out in a adiabatic process or a adiabatic condition. That means to conclude this Carnot cycle, so step 1 and step 2 is the expansion of the ideal gas which is placed in the cylinder on a source of heat at a temperature T2. Okay, so the T2 is the initial temperature, and from T2, from the initial temperature, so when the compression of gas is going to take place, so the temperature will change from T2 to T1. Okay, so this is what is studied in Carnot cycle. So step 1 and step 2, the expansion of ideal gas is going to take place, and in step 3 and step 4, compression of ideal gas is going to take place, and it will carry out in a isothermal and adiabatic conditions respectively. That means in step 1 it is a isothermal process, and step 2 is a adiabatic process where we see the expansion of the ideal gas, and in step 3, so we see the compression of the ideal gas which will be in isothermal condition, and in step 4 the compression of the ideal gas and which reaches again to the initial state, so that will be carried out in the adiabatic condition or adiabatic process. Okay, so this is what we saw, and we also derived a equation where we are going to find out the efficiency of the heat engine. Okay, so the efficiency of the heat engine is defined as, so the amount of heat which is converted into work divided by the total amount of heat absorbed. Okay, so when a source or the ideal gas is going to absorb some amount of heat energy, not all the absorbed heat energy is not going to be utilized for the work done, but some part of the heat is left behind from the system or from the source. So that is the difference between how much amount of heat has been absorbed by the system and how much amount of heat has been utilized for the work done, how much amount of heat has been converted into work. So this difference gives us the efficiency of the heat engine. Okay, so this is what we derived in our previous class with the help of Carnot cycle, and also we saw a new scale of temperature which was given by Lord Kelvin. Okay, so generally speaking, so the temperature depends on the nature of the working substance. Say for example, if we take a normal mercury temperature or a thermometer, So the mercury thermometer, it depends on the expansion of mercury, whereas Lord Kelvin, he defined the temperature scale which was independent of nature of the substance. It depended only on the temperature, that is working temperature of the source and the sink, but it is independent and it does not depend upon the nature of the working substance. So this is what is called as the thermodynamic scale of temperature. Okay, so by using that, we also applied this thermodynamic scale of temperature to the Carnot's engine efficiency, and we derived a new equation which was similar to the efficiency equation, and we concluded that from the Carnot's engine's efficiency, it was very clear that when T1 is equals to 0, that is the final temperature of the heat engine is equals to 0, then the efficiency of the Carnot's engine is unity. Okay, so this is what we understood by seeing the thermodynamic scale of temperature, and then we saw Carnot's theorem. Based on this thermodynamic scale of temperature, we gave a definition of Carnot's theorem. So that is, the efficiency of a reversible heat engine depends only upon the temperature of the source and the sink and is independent of the nature of the working substance. In other words, so all reversible heat engines working between the same two temperatures have the same efficiency. Okay, so this is where we stopped in our previous class, and in this session we are supposed to discuss about the new term which is introduced in second law of thermodynamics, that is entropy. Okay, so in first law of thermodynamics we studied about enthalpy, and in second law of thermodynamics we are going to study and understand about a new term, that is what is called as entropy. So what is meant by entropy? Entropy is a thermodynamic state function. What is meant by a state function? A state function means so whose value depends upon only the initial and final state, but it does not depend upon the path which it is going to follow, the path which it is going to go through. Okay, so that is why it is called as a state function. Entropy is a measure of randomness or disorder of the molecules of that system. So the second law of thermodynamics itself, it explains that so not all the heat energy which has been supplied to the system is used for the work done, whereas some part of heat energy is going to be lost. Okay, so that heat energy is sent to the sink. So how much amount of heat has been utilized or converted into work done divided by how much amount of heat has been absorbed. So this is what is called as the second law of thermodynamics, or the efficiency of a heat engine. Okay, so that means here there is a loss, there is a disorder, some amount of heat energy has not been utilized for work done. So how much amount of randomness or disorder, or how much amount of heat has been passed to the sink without utilizing for the work done, so that is measured in terms of entropy. Okay, so the symbol which we are going to use to represent entropy is capital S. So capital S represents entropy. For a reversible change taking place at a fixed temperature, that is T, the change in entropy, that is delta S, is equal to the heat energy absorbed divided by the temperature. Okay, so this is how we are going to define entropy. Entropy, or the change in entropy, delta S, is equals to the equal the heat energy which has been absorbed. Okay, so Q is the heat energy, we represent Q. So Q is the symbol which is used to represent the heat energy absorbed by the system divided by temperature, or it can also be written in a derivative form, that is a derivation form, that is ds is equal to dq divided by T. Okay, so where dq is the heat energy absorbed divided by the temperature. The unit of entropy and entropy change is joule per Kelvin per mole. Okay, so this is how we are going to define entropy. Next, moving on to the derivation of an expression for entropy from Carnot cycle. So here we are going to prove that entropy is a state function. That means it is independent. So where the state variables which are independent, so they are called as state functions. Okay, so now let us take, for a Carnot engine, the efficiency is given by the relation nu is equals to Q2 minus Q1 divided by Q2, which is equals to T2 minus T1 divided by T2. Okay, so that means here the the amount of heat energy which is absorbed in the final state minus the amount of heat energy absorbed in the initial state divided by the total amount of heat energy supplied to the system gives us the efficiency value. Okay, so by rearranging this equation, so I can also write it in this way: 1 minus q1 divided by q2 is equals to 1 minus t1 divided by t2. Okay, so here the sign interconvention is done. Okay, so that means, so here if we write it like this, so this gives the same equation, that is if we cross multiply this, so q2 minus q1 divided by q2. Okay, so on rearranging this equation, so we are going to get q1 divided by t1. So just we are interchanging numerator and denominator, or we are doing the cross multiplication here, so this gives us q1 divided by t1. Okay, so this is q1 divided by t1 and q2 divided by t2. If heat absorbed is taken as positive, heat loss to the sink is taken as negative. Okay, so here if the heat absorbed, the how much amount of heat has been absorbed is taken as positive, and the amount of heat lost to the sink is taken as negative. Now substituting the sign conventions, we are going to get, so minus, so for the same equation, for this equation we are substituting the sign convention, that is if we add this equation is going to change, or it can also be written in this way by interchanging the right hand and left hand side. So we can interchange the sign convention, that is the summation of q divided by t will be equal to 0. Okay, in general, for a reversible cycle ABA consisting of a series of Carnot cycle, the above expression takes in the form. So we are going to integrate the above expression. So if we do the integration of the above expression, so just like how we have seen here, so here we are going to write it in a derivative form. So here ds is equals to dq divided by t. In the same way here, so this equation takes up the form that integration of dq divided by t will be equal to 0. Since the cycle is performed in 2 steps, so here this cycle is of 2 steps, that is A to B and B to A, and here A to B is called as path 1 and from B to A is called as path 2. Okay, so now the change in entropy, that is delta S is equals to if we sum up the two paths. Okay, so the two paths, that is path 1 and path 2, if we add the change in entropy delta S, or the entropy change in path 1 and entropy change in path 2, we are going to get delta S. Okay, so now what we are going to do is so here we are going to apply the integration into the path 1 and path 2. Okay, so we can write it as so here the integral form that path takes place from A to B will be written as dq divided by t of path 1 plus the integral form from B to A. So this is from B to A dq divided by t of path 2 will be equal to 0. Okay, so now delta S is equals to, if I take this towards the right hand side, it takes the negative sign. Okay, so it will take a negative sign. So delta S is equals to, so I can write it as so integral form from A to B dq divided by t of path 1 will be equal to A to B. So because here I am interchanging it, so that is why the negative sign is going to removed, and I can write it in this way. Okay, so from this equation, so it follows that the entropy change during the change from A to B along path 1 or path 2 is same, because here path 1 is equals to path 2. So both are same. The entropy change in path 1 will be equal to the entropy change in path 2. Both are same. In other words, so the entropy change is independent of the path taken, and hence it is considered as a state function. Okay, so this is how we are going to prove that entropy is a state function, and this is the derivation of an expression for entropy from Carnot's cycle. Okay, and our next part of discussion is physical meaning of entropy. So how we can understand entropy in terms of physical reactions. So this path, the example what we have taken here, all these are imaginary paths or imaginary reactions which is going to take place. But how to understand entropy? By taking physical examples, or the physical meaning of entropy is understood by understanding the entropy and disorder, and also the entropy and available energy. Okay, so now we will see the first one. In the physical sense, entropy of a system can be taken as a measure of disorder. Okay, so this is what I told while defining entropy. Entropy means it is a measure of disorder. Disorder means so how much amount of energy or heat has been used or converted into work done, and how much is left without using to work done. Some amount of energy is left behind the sink. How much energy has been left and how much energy has been converted into work. So that measure is called as the entropy. So to prove this, the following examples can be considered. The first one, so in all solids, the ions, atoms or molecules are arranged in a regular way in the form of a lattice. Okay, so if you have seen the structure of ice, so there you will understand. So all the water molecules are arranged in a exact crystal lattice manner. Okay, so the difference between the each molecules or atoms will be the same. They are arranged in a regular way in the form of lattice. When the solid is melted, that is when ice is going to melt, the particles forming the lattice become free. That means all the molecules, that is hydrogen and oxygen, so they are going to get separated, or they will become free. Okay, so whereas in case of ice, when they are in the form of ice, so there is a regular way in the form of lattice, whereas when the solid is melts, the particles forming the lattice become free and order is lost. There is no order, there is no exact distance between the two molecules or two ions or atoms is absorbed. So that is why when order is lost, then definitely disorder increases. Hence entropy increases during melting of solids. Okay, so when ice melts and converts into a liquid, so their disorder is going to increase. And when the liquid converts into gaseous form, so then again the disorder is going to get increase. Okay, so that is why we say that so when there is a change in the state from solid to liquid, so there we will find the particles forming the lattice will become free, and here order is lost and disorder increases. Hence entropy increases during melting of solids. Okay, and the second example is during spontaneous changes like expansion of a gas, diffusion of a gas, etc. So disorder is going to increase. Okay, so the same example which I took while explaining the Joule-Thomson's coefficient, Joule-Thomson's experiment. So they when a gas which is in the higher pressure is blown towards the lower pressure, definitely the gas molecules will have more space to move towards, and there the order is lost. When order is lost, there is a increase in the disorder and entropy also increases. Hence during all spontaneous process, entropy increases, that is delta S is equal to positive. Okay, so delta S means change in entropy will be positive. And the second example what we can take to understand the physical meaning of entropy is entropy and available energy. The energy which can be converted into useful work is called as available energy, whereas the remaining portion of energy which cannot be converted into useful work is called unavailable energy. So this is very simple. So the energy which is converted into a useful work, so that is called as available energy, and the remaining portion of energy which cannot be converted into useful work is called as unavailable energy. Entropy is regarded as a measure of unavailable energy. Entropy is a measure of unavailable energy. When entropy S is multiplied by the temperature T, the product Ts is the amount of unavailable energy which cannot be converted into useful work. Okay, so here we are defining unavailable energy. What is meant by unavailable energy? So unavailable energy means when the entropy S is multiplied by the temperature T, the product Ts is the amount of unavailable energy. Then out of total energy absorbed by a system Q, the amount less by Ts will represent the available amount of heat which can be converted into useful work. Thus the available energy X can be put as X is equals to Q minus Ts. Okay, so X is equals to Q minus Ts. So this is how we can understand the entropy and available energy, which helps us to define the physical meaning of entropy. And next is so let us see entropy change of an ideal gas with change in pressure, volume and temperature. So the first case is variation of entropy with volume and temperature. The infinitesimal change in entropy, that is ds, is equals to dq divided by T. Okay, so this is the definition of change in entropy. So here if you see, so we defined entropy, so delta S ds is equals to dq divided by T. The same thing here we are taking, ds is equals to dq by T. Okay, so this is the change in entropy. From the first law of thermodynamics we have, so this is the first law of thermodynamics equation, that is dE is equals to dQ minus dW. But we know that dE is equals to CV dt and dW is equals to PdV. So these all derivations we have done in our previous class. You go through in your textbook, you go back and see in your textbook, so you will understand it. Okay, so we have defined that the change in internal energy dE is equals to CV, that is molar equation, that is what is that, what is meant by CV. So CV is the molar heat capacity at constant volume. Okay, so molar heat capacity at constant volume, dt, and dW is equals to PdV. Substituting this value dE, substitute dE value here and dW value here. So we are going to get, take dQ towards the right hand side, dE will go towards the right hand side, dQ will come towards the left hand side. So dQ is equals to CV dt plus PdV. Let me call this equation as 3. For 1 mole of an ideal gas, we know that PV is equals to RT. Okay, so P is the pressure, V is the volume, is equals to R is the universal gas constant, and T is the temperature. By rearranging this equation, so take PV towards the left hand side, P is equals to RT divided by V, and let me call this equation as equation number 4. From equation 3 and 4 we have, so equation 3 is dQ is equals to CV dt plus PdV, and equation 4 is P is equals to RT divided by V. Substitute that equation in dQ, so we will get equation number 5. Okay, so next what we have to do is, so we have to divide the equation number 5 by T. When we divide equation number 5 by T, we are going to get dQ divided by T, which is equals to CV dt divided by T plus R dV divided by V. Let me call this equation as 6. From equation 1 and 6, so this is the equation 6, and from equation 1 and 6 we have, so ds, that is change in entropy, is equals to CV dt divided by T plus R dV divided by V. Let me call this equation as 7. So let us system change from state 1 to 2. So now the system is changing from state 1 to 2. That state might be our initial state and a final state. Okay, so there is a change in state. So from 1 to 2 the system is changing its state. So when it changes its states, all the values like entropy, temperature and volume are also going to change from one state to the second state, that is the corresponding change in entropy, temperature and volume be S1. So S1 means entropy, S is represented as means entropy is represented by the symbol capital S. S1 means, so this is the entropy of the system at state 1. So from state 1 to state 2 it is changing, so that is why from S1 to S2, and the temperature is changing from state 1 to state 2, so that is why I am writing it as T1 to T2, and volume is changing from state 1 to 2, so that is why I am writing it as V1 to V2 respectively. To obtain the change in entropy delta S, so equation 7 is integrated between the respective limits. Okay, so respective limits means, so here S1, S2, T1, T2, V1, V2. So these are the limits which we are going to use to integrate between the change in entropy. Okay, so delta S from limit 1 to 2 is equals to CV to the integral form of T1 to T2 limit T1 to T2 dt divided by T plus R limit V1 V2 into dV divided by V. Okay, so now removing these limits, so I can write it as S2 minus S1, which is equals to CV ln T2 divided by T1 plus R ln V2 divided by V1. Okay, so if I write this change in entropy, that is S2 minus S1 as delta S. So delta S is the change in entropy. So this is the equation what I am going to get. So equation 8 gives the entropy change of 1 mole of an ideal gas accompanying the process when temperature changes from T1 to T2 and volume changes from V1 to V2. Okay, so this is how we are going to study the entropy change of an ideal gas with the variation of entropy with volume and temperature. And the second case is the variation of entropy with pressure and temperature. So here also the same thing we are going to do. So the ideal gas equation can be applied to the initial and final states of the system containing 1 mole of a substance. So hence for the initial state P1 V1 is equals to RT1 and for the final state P2 V2 is equals to RT2. So divide the equations, divide the two equations to get. So if you divide these two equations, we are going to get equation number 9. But we have Cp minus Cv is equals to R, or it can also be written as Cv is equals to Cp minus R. So from equations 8, 9 and 10, if we substitute the values of Cp, Cv and Cv in the equation, we are going to get delta S is equals to, so Cp minus R ln T2 divided by T1 plus R ln P1 T2 divided by P2 T1. Okay, so here we are just substituting the values of equation 8, 9 and 10. If you see, if you go back and see the equations 8, 9 and 10, just substitute these equations, we are going to get the delta change or the entropy change in the variation of entropy with pressure and time. Okay, so here, so this is the simplified form of the equation. So this equation 11 gives the entropy change of 1 mole of an ideal gas accompanying a process when a temperature changes from T1 to T2 and the pressure changes from P1 to P2. Okay, so this is how we are going to understand the entropy change of an ideal gas with a change in pressure, volume and temperature. So in my next class we will discuss about the entropy change of an ideal gas in different process. Okay, so different process like isochoric process, isobaric process, isothermal and adiabatic process, how the entropy change is going to take place. So all these will be discussed in our next class. Thank you, dear students.